There is a second notion of vector multiplication that is common, especially in the context of engineering, physics, and computer graphics. This product is the cross product. The cross product is very useful in three-dimensional linear algebra, but it does not have a generalization to higher dimensions. Geometrically, the cross product of two vectors, v and w, is a vector that is orthogonal to both v and w, and has magnitude of v times magnitude of w times sine of theta, where theta is the angle between v and w. Note that, unlike the dot product, the output of a cross product is a vector, not a number. Let's look at this definition a bit more closely. Notice that if theta is 0 or pi, that is 0 or 180 degrees, then the cross product will have magnitude 0. So in other words, the cross product of two parallel vectors is the zero vector. Also, if either v or w is the zero vector, then the cross product will be the zero vector as well. Assuming we're not in one of these degenerate cases, notice that there are in fact two vectors that meet the geometric description given so far. These vectors are negatives of each other. In order to determine which vector to use, we proceed by the right-hand rule. Here's how the right-hand rule works. If the cross product is v cross w, imagine your right thumb pointing in the direction of v, and your right index finger in the direction of w. Then extend your right middle finger, and then the direction it points will be the direction of v cross w. So in this case, it will be pointing up. Notice that if we switch the order of the cross product to w cross v, then using the right-hand rule will give us the downward pointing vector. This gives us the equation v cross w equals the negative of w cross v. Because switching the order of multiplication negates the product, we call the cross product anti-commutative as opposed to the commutative dot product, in which switching the order does not affect the product. A consequence of this geometric formula can be seen in the parallelogram spanned by v and w. Take the length of the v arrow to be the base of the parallelogram. Then the height of the parallelogram is the length of this segment from the head of the w arrow to the line spanned by v perpendicular to v. Using the trigonometric identity, sine of theta equals opposite over hypotenuse, which is the SO from SOHCAHTOA, we have that the sine of theta equals the height divided by the length of w. In other words, the length of w times sine of theta equals the height of the parallelogram. Remembering that the area of a parallelogram is base times height, this means that the area of this parallelogram is the magnitude of v times the magnitude of w times sine of theta. In other words, it's the length of v cross w. Another geometric note is that the area of this triangle spanned by v and w is exactly 1/2 of the area of the full parallelogram. That means the area of the triangle will be 1/2 times the magnitude of the cross product. Again, all this is great, but it's of little use to us without a practical formula for the cross product. So, given vectors v with coordinates x1, y1, z1, and w with coordinates x2, y2, z2, here is such a formula. The cross product of v and w is the vector, first coordinate, y1 times z2 minus y2 times z1, second coordinate, it's the negative of the quantity x1 times z2 minus x2 times z1, and the third coordinate is x1 times y2 minus x2 times y1. So, for an example, if we wanted to find the cross product of the vectors v, which is 5, 3, minus 2, and w, which is minus 1, 0, 3, then we would compute first coordinate 3 times 3 minus 0 times negative 2, second coordinate negative quantity of 5 times 3 minus negative 1 times negative 2, third coordinate 5 times 0 minus negative 1 times 3. And that would give us the vector 9, negative 13, 3. One way to help confirm that we did our arithmetic correctly is by checking that our outcome is orthogonal to both of our vectors v and w. The dot product of v with the cross product will be 45 minus 39 plus 6, which is 0. And then the dot product of w with the cross product will be negative 9 plus 0 plus 9, which is 0. So our result is orthogonal to both v and w. We can also use our cross product to find the area of the parallelogram spanned by v and w. To do this, we would take the magnitude of our cross product, which would be the square root of 9 squared plus negative 13 squared plus 3 squared. Computing this gives us approximately 16.093.